Hey everyone, and welcome to a deep dive all about atoms. We're going to be taking a look at how our understanding of the atom has evolved over time.
Yeah, from those really early philosophical ideas to, the kind of mind-blowing discoveries of modern science.
Exactly. And I, for one, can't wait to, unpack it all with you. So
Okay.
where do we even begin?
Well, I think the best place to start is way back in ancient Greece and India.
Oh, wow. So we're going that far back.
Yeah, like around 400 BC, thinkers back then were already grappling with this idea of what makes up the world around us, and they came up with this concept of the atom. They thought of it as this fundamental, indivisible particle like the smallest possible piece of matter.
So basically like the ultimate building block.
Exactly. They even called it an atom because the word atom comes from the Greek word atomio, which means uncuttable or non-divisible.
Wow, the ancients were really onto something. But did they have any actual proof for this idea, or was it mostly like philosophical speculation?
It was pretty much pure speculation for centuries, actually. They didn't have the tools or the technology to really investigate matter at that level.
I see. So how did we go from those ancient musings to, an actual scientific theory of the atom?
Well, fast forward to the early 1800s, and a British chemist named John Dalton comes into the picture.
Ah, Dalton. I remember learning about him in school. Wasn't he the one with the atomic theory?
That's the one. Dalton's atomic theory was really a turning point. He was able to explain a lot of those fundamental chemical observations.
Like what kind of observations?
Well, for example, he explained why matter is conserved in chemical reactions. Like if you burn a piece of wood, the total mass of the ashes and the smoke and the gases released will still equal the mass of the original wood.
Right. Matter can't be created or destroyed, just transformed.
Exactly. And Dalton's theory explained that beautifully. He also explained the law of constant composition. This law says that a given chemical compound always contains the same elements in the same proportions by mass.
So like water is always 2 parts hydrogen to 1 part oxygen, no matter where the water comes from.
Precisely. So Dalton's theory was really a game changer. But like any scientific theory, it had its limitations.
I'm guessing it wasn't the full picture, right?
Yeah, exactly. Dalton's model was based on the idea that atoms were these solid, indivisible spheres. But scientists started to notice some phenomena that just didn't fit with this picture.
Oh, like what?
Well, things like static electricity, for example. If atoms were truly indivisible and solid, then where did those electrical charges come from? How could they be transferred from one object to another?
Good point. It sounds like the atom was about to get a whole lot more interesting.
You got it. And one of the first clues came from experiments with a device called a cathode ray tube.
Cathode ray tube, that rings a bell. Didn't those play a role in the discovery of electrons?
Yes. Cathode ray tubes were these glass tubes that had most of the air pumped out of them. And when a high voltage was applied across the tube, it produced this beam of mysterious rays.
Mysterious. In what way?
Well, scientists weren't sure what these rays were made of at first, but J.J. Thomson, a British physicist, conducted some really clever experiments with these tubes. And through those experiments, he was able to demonstrate that these rays were actually streams of negatively charged particles. He called them corpuscles at the time.
But we now know them as.
Electrons. And this discovery was monumental.
Yeah, it meant that atoms weren't those indivisible spheres that Dalton had envisioned.
Right. They actually had a substructure and contained these tiny particles that were much, much smaller than the atom itself.
Wow, a truly groundbreaking discovery. I
Yeah.
mean, think about it. These tiny electrons are a fundamental component of every single atom in the universe. That's mind-blowing.
It really is. And Thomson was even able to determine the charge-to-mass ratio of these electrons using his experiments.
And then a little later, Millikan figured out the absolute charge of an electron.
Yes. With his oil drop experiment, it was a really ingenious experiment, and it allowed us to determine the mass of the electron as well.
Wow, so much progress was happening in such a short amount of time. So we had electrons, but I'm guessing the story doesn't end there, right?
Oh, there's so much more to come. After the discovery of electrons, scientists went on to discover other subatomic particles as well.
Like protons and neutrons.
Exactly. Protons carry a positive charge and neutrons have no charge.
Mm.
So now we had these three fundamental particles, but the question remained, how are they arranged within the atom?
So we knew the ingredients, but not the recipe.
Right. And this is where one of the most famous experiments in physics comes in, Rutherford's gold foil experiment.
Ah, yes. Rutherford's gold foil experiment. I remember learning about that in school, but I'll admit, it always seems more like a historical anecdote than a pivotal scientific discovery.
Well, let me tell you, it was a lot more than just a story. It completely revolutionized our understanding of the atom.
Okay, I'm all ears. Tell me about this experiment and why it was so groundbreaking.
So at the time, the prevailing model of the atom was Thomson's plum pudding model.
Plum pudding. That's an interesting name for an atomic model.
It is, but it kind of made sense at the time. Imagine a plum pudding where the plums represent the negatively charged electrons, and the pudding itself represents this positively charged soup that the electrons were embedded in.
Okay, I can kind of visualize that. So
Yeah.
how did Rutherford's experiment challenge this model?
Rutherford's team decided to probe the structure of the atom by firing alpha particles at a very thin sheet of gold foil.
Alpha particles, what are those exactly?
Alpha particles are essentially helium nuclei. They consist of 2 protons and 2 neutrons, and they have a positive charge.
Got it. So they fired these positively charged alpha particles at the gold foil. What happened?
Well, if the plum pudding model was correct, they expected the alpha particles to pass right through the foil with maybe just a slight deflection here and there.
Makes sense. If the atom was mostly this diffuse, positively charged pudding with tiny electrons scattered throughout, it wouldn't offer much resistance to the alpha particles.
Exactly. But that's not what happened at all. They were absolutely stunned by the results.
Oh, what did they observe?
Most of the alpha particles did pass straight through the foil as expected. But here's the mind-blowing part. Some of the alpha particles were deflected at very large angles, and a small fraction of them, a tiny but significant fraction, actually bounced straight back.
Bounced straight back. That's incredible. It's like they were hitting something solid within the gold foil.
Exactly. And this is what led Rutherford to propose his nuclear model of the atom.
The nuclear model. So this is where we get the idea of the atom having a nucleus.
You got it. Based on the results of his experiment, Rutherford concluded that most of the atom's mass and all of its positive charge was concentrated in a tiny, incredibly dense central region, what he called the nucleus.
So the atom wasn't this diffuse pudding after all. It had a tiny, massive core.
Exactly. And he proposed that the electrons were scattered around this nucleus, occupying a much larger volume of space.
Wow, this completely changed our picture of the atom. So the atom was mostly empty space with a tiny but massive nucleus at its center.
That's the picture that emerged from Rutherford's groundbreaking experiment. And it has stood the test of time, forming the basis of our understanding of atomic structure even today.
Amazing. But I have to ask, if the electrons are negatively charged and the nucleus is positively charged, wouldn't the electrons just spiral into the nucleus? Wouldn't the atom collapse in on itself?
That's a brilliant question, and it highlights a major limitation of Rutherford's model. Classical physics simply couldn't explain how atoms could be stable if they were structured this way. According to classical physics, accelerating charged particles, like electrons orbiting a nucleus, should emit electromagnetic radiation and lose energy, causing them to spiral inward.
So Rutherford's model, while revolutionary, couldn't explain the stability of the atom.
Exactly. And this is where our story takes another fascinating turn. We need to move beyond classical physics and into the realm of quantum mechanics to understand how atoms can exist as stable entities.
This is getting exciting. It sounds like we're about to dive into a whole new world of physics to solve this atomic mystery.
We are. But that'll have to wait for our next installment. Welcome back to our deep dive into the atom. Last time we kind of left off with this puzzle, How can atoms be stable if the electrons are supposed to be whizzing around a positively charged nucleus?
Right, because according to classical physics, those electrons should be losing energy and spiraling inwards.
Exactly. And that's where things start to get really interesting, because to solve this puzzle, we need to step outside the realm of classical physics.
Okay, so what's the solution? How do we explain the stability of the atom?
Well, it turns out that at the atomic level, the rules of the game change. We need to enter the strange and fascinating world of quantum mechanics.
Quantum mechanics. That always sounds a bit intimidating.
I know it can seem that way, but it's really not as scary as it sounds. In fact, it's one of the most successful and well-tested theories in all of physics.
Okay, so how does quantum mechanics help us understand the atom?
Well, one of the key ideas in quantum mechanics is that energy at the atomic level isn't continuous, but exists in these discrete packets called quanta.
Quanta. So instead of energy being this smooth flow, it comes in these tiny, specific bundles.
Exactly. And this idea was first proposed by Max Planck in the early 1900s. He was studying something called black body radiation.
Black body radiation.
That's basically the way objects emit light when they're heated.
Okay, I can picture that. So what does this have to do with atoms?
Well, Planck found that he could only explain the observed patterns of blackbody radiation if he assumed that the energy of the light waves was quantized, meaning it could only exist in these discrete multiples of a fundamental unit of energy.
So like steps on a ladder. You can only be on one step or another, not somewhere in between.
A perfect analogy. And this idea of quantized energy was revolutionary because it went against everything classical physics had taught us.
Right. In classical physics, energy was thought to be continuous. You can have any amount of energy, big or small.
Exactly. But Planck's work showed that at the atomic level, this wasn't true. And this paved the way for a whole new understanding of the atom.
So how did this idea of quantized energy help explain the stability of the atom?
Well, a young Danish physicist named Niels Bohr took this idea of quantized energy and applied it to the atom. He developed a model of the atom that incorporated this quantum behavior.
Bohr's model. I remember learning about that in school. Didn't it involve electrons orbiting the nucleus in specific energy levels?
That's it. Bohr proposed that electrons in an atom could only exist in certain discrete energy levels, or shells. Each of these energy levels corresponded to a specific distance from the nucleus.
So instead of being able to orbit at any distance like planets around the sun, electrons were restricted to these specific energy levels.
Precisely. And this was a huge departure from the classical picture. Bohr's model said that electrons couldn't exist anywhere in between these allowed energy levels.
So kind of like those steps on a ladder again.
Exactly. And here's the crucial part. As long as an electron was in one of these allowed energy levels, it wouldn't radiate energy and spiral into the nucleus.
I see. So Bohr's model provided a way for atoms to be stable.
Exactly. His model explained why atoms didn't just collapse in on themselves. It was a major breakthrough.
It sounds like it. But Bohr's model also explains something else, right? Something about the light that atoms emit.
Yes, Bohr's model beautifully explained the observed line spectra of elements.
Line spectra. Remind me what those are again?
So when you heat up an element, it emits light, right?
Yeah.
And if you pass that light through a prism, you can split it into its different colors.
Like a rainbow.
Right, but what's interesting is that you don't see a continuous spectrum of colors like a rainbow. Instead, you see these discrete lines of color at very specific wavelengths.
So it's more like a barcode than a rainbow.
A perfect analogy. And each element has its own unique line spectrum, its own unique barcode.
And Bohr's model explained these line spectra.
Yes. Bohr proposed that when an electron jumped from a higher energy level to a lower energy level, it emitted a photon of light.
A photon? Isn't that a particle of light?
Exactly. And the energy of that photon corresponded to the difference in energy between the two energy levels.
So each line in an element spectrum corresponds to a specific electron transition between energy levels. That's amazing.
It is. Bohr's model provided a really elegant explanation for these line spectra, which had been a mystery for a long time.
So Bohr's model was a huge step forward in our understanding of the atom. But I'm guessing it wasn't the final word, right?
Right. As successful as Bohr's model was, it had its limitations. It couldn't fully explain the spectra of more complex atoms with more than one electron. And it also had some other issues. For example, it treated electrons as if they were these tiny particles orbiting the nucleus in well-defined paths.
We were talking earlier about the wave-particle duality of matter. So electrons can act like waves too, right?
Exactly. And that's where Bohr's model starts to break down because it doesn't take into account the wave-like nature of electrons.
So we need a model that can accommodate both the particle-like and the wave-like nature of electrons.
Precisely. And that's where things get even more interesting because we need to move beyond this picture of electrons orbiting the nucleus in well-defined paths.
It sounds like we're about to enter a realm where things get a lot fuzzier and less certain.
You got it. We're about to dive into the heart of quantum mechanics, where probabilities and wave functions become the tools of the trade.
Welcome back to our deep dive into the atom. We've come a long way, from those ancient Greek philosophers to those revolutionary experiments of the early 20th century, and now we're venturing into the quantum realm. Last time we kind of left off with this idea that electrons can act like waves and that Bohr's model couldn't quite capture that wave-like behavior.
Right, and that's where things start to get really mind-bending because we have to abandon this classical picture of electrons orbiting the nucleus in neat little paths.
So if electrons aren't orbiting the nucleus like planets, how do we even describe their behavior? Where are they in the atom?
Well, in the quantum mechanical model of the atom, we can't talk about the exact location of an electron.
I can't. Why not?
Because of Heisenberg's uncertainty principle. It's one of the most fundamental principles in quantum mechanics. And it basically says that there's a limit to how precisely we can know both the position and the momentum of a particle at the same time.
So the more we try to pinpoint an electron's location, the less we can know about its momentum and vice versa.
Exactly. It's like trying to catch a firefly in your hand. The moment you close your hand around it, it's already moved somewhere else.
I see. So if we can't know exactly where an electron is, how do we describe its behavior in the atom? Do we just throw up our hands and say, it's all uncertain?
Not at all. Instead of talking about precise locations, we talk about probabilities.
Probabilities.
Yes. In quantum mechanics, we describe the state of an electron using something called a wave function.
A wave function.
Yeah, and the wave function doesn't tell us exactly where an electron is, but rather it gives us information about the probability of finding it in a particular region of space.
So instead of pinpoint locations, we have regions of probability.
Exactly. It's like saying we know the cloud where it's most likely to rain, but we can't predict exactly which raindrops will land where.
Okay, that makes sense.
Yeah.
But how do those probabilities relate to the structure of the atom?
Well, in the quantum mechanical model of the atom, those wave functions of electrons are called atomic orbitals.
Atomic orbitals, are those kind of like the orbits in Bohr's model?
They're similar in that they describe the regions of space where electrons are most likely to be found. But unlike those neat circular orbits in Bohr's model, atomic orbitals are three-dimensional shapes defined by mathematical equations.
Three-dimensional shapes. So they're not just those flat circles anymore.
Right. They can be quite complex. They come in different shapes and sizes, and each orbital can hold up to 2 electrons.
2 electrons per orbital. Is there a reason for that?
Yes. It's because of another important principle in quantum mechanics, the Pauli exclusion principle.
The Pauli exclusion principle.
Yeah, it states that no 2 electrons in an atom can have the same set of 4 quantum numbers.
Quantum numbers, what are those?
Those are really the key to understanding how electrons are arranged in atoms. Each orbital is characterized by a unique set of 4 quantum numbers. These numbers act like an address, telling us the energy, shape, and orientation of each orbital.
So it's like each electron has a unique set of coordinates within the atom.
Exactly.
Okay, tell me more about these quantum numbers. What do they represent?
Well, the first one is the principal quantum number, which is denoted by the letter N. This number tells us the energy level or shell that an electron occupies. The higher the value of N, the higher the energy level, and the further the electron is, on average, from the nucleus.
So it's kind of like floors in a building, higher floors mean higher energy levels for electrons?
Yeah. Then we have the azimuthal quantum number, denoted by the letter L, which tells us the shape of the orbital.
So different shapes for different orbitals.
Right. For example, when L equals 0, we have spherical orbitals called s orbitals. When L equals 1, we have dumbbell-shaped orbitals called p orbitals. And when L equals 2, we have even more complex shapes called d orbitals.
So it's like a set of building blocks with each type of orbital having a unique shape.
Exactly. And then we have the magnetic quantum number, denoted by ML, which tells us the orientation of an orbital in space. For a given value of L, ML can take on 2L plus 1 values, ranging from LL to plus L.
So those dumbbell-shaped p orbitals can be oriented along different axes in three-dimensional space.
You got it. And finally, we have the spin quantum number, denoted by EMS, which describes the intrinsic angular momentum of an electron.
So electrons are actually spinning.
Well, it's not exactly spinning in the classical sense, but it does have this intrinsic angular momentum called spin, which can be either up or down.
Okay, so even within a single orbital, we have this added complexity of electron spin.
Right. And because of the Pauli exclusion principle, if 2 electrons occupy the same orbital, they must have opposite spins.
So each orbital can hold a maximum of 2 electrons with 1 spin up and 1 spin down.
Exactly. And these 4 quantum numbers, N, L, ML, and EMS, give us a complete address for each electron within an atom.
It's amazing how much information is packed into those 4 little numbers.
It really is.
Mm-hmm.
And they're crucial to understanding how electrons are arranged within atoms. But it gets even more interesting because there are rules that govern how electrons fill those atomic orbitals as we move across the periodic table.
Okay, so how do we build up the electronic structure of atoms? How do we know which orbitals get filled first?
Well, the first rule we need is the Aufbau principle, which basically means building up in German. This principle states that electrons fill atomic orbitals in order of increasing energy.
So it's like building a house, starting with the foundation and then adding floors one by one.
Yeah, Electrons, being lazy like the rest of us, want to be in the lowest energy state possible, so they'll feel those lower energy orbitals first.
But what happens when we encounter orbitals that have the same energy? Which ones get filled first?
That's where Hund's rule comes in.
Hund's rule.
Yeah, it basically says that when you have multiple orbitals with the same energy, electrons prefer to occupy them singly with parallel spins before they start pairing up in the same orbital.
So they like to spread out and have their own space before they start sharing rooms.
Exactly. And this is because electrons repel each other, so spreading them out minimizes those repulsive forces and leads to a more stable configuration.
So all of these principles and quantum numbers are like the rules of the game for how electrons are arranged in atoms.
Exactly. And those arrangements, in turn, determine the chemical properties of the elements. They dictate how atoms interact with each other, how they bond and react.
Wow, so all of this seemingly abstract stuff about quantum numbers and orbitals actually shapes the world around us.
It does, and it's truly remarkable to think that the behavior of matter at the macroscopic level is ultimately governed by these quantum mechanical principles operating at the atomic level.
It's been an incredible journey exploring the atom with you. From those early philosophical ideas to the mind-boggling world of quantum mechanics, we've seen how our understanding of this fundamental building block of matter has evolved over centuries of scientific inquiry.
And the journey is far from over. There's still so much we don't know about the atom and about the universe at large, but thanks to the power of scientific inquiry, we're constantly pushing the boundaries of our knowledge.
I'm leaving this deep dive with a sense of awe and wonder about the intricacies of the atom, and a profound appreciation for the scientists who have dedicated their lives to unraveling its mysteries. I encourage all of our listeners to keep exploring, keep questioning, and keep that spark of curiosity alive, because who knows what amazing discoveries await us in the future.